every year, the Institute of Mathematical Statistics distinguishes 3 probabilists, and they recommend them with a medallion and ask them to deliver one of the medallion lecture, which takes place in a meeting sponsored by the IMS. And I'm very happy that David Nualart from Kansas University will be one of the recipients of this medallion. So you. So David is a remarkably prolific and important contributor to stochastic analysis. His work covers a wide array in this topic, and in particular on Malliavin calculus, Gaussian processes, Gauss expansion, stochastic differential equation, backward stochastic differential equations. I could name many more, but time is short, and I give David present his lecture on Malliavin calculus and normal approximation.
You hear me? Okay, thank John for this kind introduction. It's a great honor and also a pleasure for me to present this lecture here. So I'm going to talk about Malliavin calculus, of course, and normal approximations. So Malliavin calculus was introduced by Paul Malliavin in the 70s, and it's calculus of variations with respect to the trajectories of Brownian motion. And the purpose was to provide the probabilistic proof of Hormander's hyperplasticity theorem. Later, this calculus was developed by many people. Among them, I'd like to mention Bismuth, Dijkstrup, Kusuoka, Watanabe, and others. And what was the purpose of this calculus? Essentially, the idea is the following. You are given a Gaussian process, you're given a random variable, which is a function of the Gaussian process, and you want to know if this random variable has a density, and if the density is smooth. So the idea is, the main application is to show the existence and the smoothness of densities for functionals of Gaussian processes. But I'm not going to talk about this here, and I will focus my lecture on some more recent applications of Malliavin calculus for normal approximations. And the idea is to combine Malliavin calculus with a classical technique, which is Stein's method. And perhaps the best reference for this is the monograph written by Ivan Nourdin and Giovanni Peccati on normal approximations with Malliavin calculus. Okay, so let me start with some notation from the beginning. So we are going to work with a general Gaussian family of random variables associated with a Hilbert space. So H is a Hilbert space, and then we have this Gaussian family X of H indexed by a Hilbert space. And we assume that the covariance is given by the scalar product of the Hilbert space, and the family is centered. We call this family H1. So H1 is going to be the first chaos, and then we can introduce, using polynomials, we can introduce chaos of higher order. So for every q integer bigger or equal than 2, we define the q linear chaos as follows. So you take the mid polynomials of order q of Gaussian random variables with norm 1, and then you take the linear span and then the closure, and you call this the chaos of order q. So it's a subspace HQ of L2. And then you have the notion of multiple stochastic integral, which I call IQ. Called IQ. So IQ is an isometry between the symmetric tensor product of H and this Q linear chaos, and this isometry maps H tensor Q into the mid polynomial HQ applied to X of H. And this can be extended to an isometry. So this linear chaos of order Q is isometric to the tensor product of H, symmetric tensor product with a modified norm. Okay, so we know what is the Q linear chaos, we know this generalized multiple integral, then that's for a general Gaussian process, but the simple example is Brownian motion. So suppose that you have just an ordinary Brownian motion dt, then in that case, the space H is just L2 of 01. And then for every H in L2 of 01, x of H is the binary integral of H with respect to the Brownian motion. So this would be your Gaussian family. And then in that case, the symmetric tensor product of H is just functions which are square integrable functions of Q variables and which are symmetric. And then this IQ, this multiple integral, is just an iterated integral of the kernel H with respect to the Brownian motion. So that's a particular case of this general framework I introduced before. Okay, so now if we assume that in our probability space C algebra generated by this Gaussian family, then you have this linear chaos decomposition, which means that L2 of omega is the orthogonal sum of the HQs, and then any random variable can be written uniquely as the expectation plus infinite sum of multiple integrals of some kernels FQ, which belong to H symmetric tensor Q. Okay, so all of this is well known. And then we're going to build the Malliavin calculus. So in the next 2 slides, I will give you a very short course on Malliavin calculus. So even if you don't know anything about Malliavin calculus, I hope it will be understandable. So, first, so we're going to define 3 operators in this context, acting on random variables. So the operators will be T, delta, and L. Okay, so T is the derivative operator. So suppose that you take a random variable first, which is take a random variable which is smooth and symmetrical. So it's a nice function of a finite number of Gaussian random variables. Then you define D of F in that way. So you use chain rule, and then the idea is that D of X of H. So you get back H. So remember the example where you have Brownian motion, and then X of H is a stochastic integral, so D is the inverse of a stochastic integral. So you get back the integral, which is H. Okay? So, and then because D is a derivative, when you have D of a function of a finite number of Gaussian, then you have this. So now you can extend this derivative. So remember the derivative is a random variable with values in H. So it's a kind of infinite dimensional gradient. And then you can now extend this to a sublevel space D12, which is a subspace of square integrable random variables with values in H. And this is the closure of S with respect to this sublevel seminorm, which is the L2 norm of F plus the L2 norm of the derivative. Okay, so that's the first operator, which is the derivative operator. So now our second operator is the divergence, which is the adjoint of D. And it's characterized by this duality relationship. So you have D of F, inner product with U, so U takes values in H, so this should be equal to the expectation of F times delta of U. So this characterizes delta of U, you have this relation for every F in D1, 2. So this is just the ordinary way in which you define the adjoint of an operator. Okay? So now we have another operator L. So what is L? Well, actually it turns out that L is the generator of the Austrian-Ulenbach semigroup, which means is just multiplication by minus Q on every linear chaos. And the L satisfies this important formula, which is delta composed with D is just minus L. So this is a fundamental formula which relates the 3 operators. Okay? And L is what is called in physics the number operator, which means multiplied by Q minus Q in a linear chaos. And then, of course, this is well defined in R2, provided that this is convergent. So now that's what we need to know about Malliavin calculus, that's all. Okay? So now after this, I'm going to prove a very simple integration by part formula that will be used later for normal approximations. So this is our next step. So I will prove an integration by part formula. To do this, let's take a random variable F, which is in the sublevel space D12, with zero expectation, and then take a function which is differentiable. And then I want to compute the expectation of a small f of f multiplied by f. And then to compute this, the idea is the following. So you take f, and because it has zero expectation, I can write f as L composed with L minus 1 of f. L minus 1 is the inverse of f, which is well defined because f has zero expectation. And then I use that L is minus delta d. So this means that this is minus delta d L minus 1 of f. It's a very complicated way to write f. Okay? F is equal to minus delta d of L minus 1 of f. So now I replace this f here by this, and you get this. Okay? And now I use the duality relationship, so this delta goes away, and you get d of f inner product with dl minus 1 of f. And then I use the Division operator, it is a differentiation, so this is the expectation of f prime of f multiplied by this inner product. Okay? So that's a very simple computation that allows you to compute the expectation of f times f in that way. Now, we will be interested mainly in random variables belonging to a fixed linear case. So let's see what happens if your random variable belongs to a fixed linear case. So suppose that h is in HQ. Then in that case, L minus 1 of f is minus 1 over q times f. Because L multiplies by q. So L minus 1 multiplies by minus 1 over q. So this is just minus 1 over q. So if you replace this here, then you get that this formula is transformed into this one. Expectation of f of f times f is 1 over q, expectation of f prime of f, and here you get just the L2 norm, the square norm of d of f in h. Okay, so this is the formula that we are going to keep in mind later. Okay, so that's enough for Malliavin calculus. Now I'm going to turn to this Staines method, and I will start with a very simple observation, which is the following. A random variable z has a normal 0-1 distribution, even only if for every test function f, the expectation of f of z times z minus f prime of z. Now you know why I have computed this before. Okay, but here z is normal 0-1, so z is normal 0-1 even only if its expectation is 0. That's an easy consequence of the differential equation satisfied by the normal density. So the idea of Staines method is the following. If this expectation is small for a large class of functions, then we can conclude that your random variable is close to the normal distribution. So this is the main idea. We're going to quantify this and assume that this is small. And then in order to do this, I'm going to introduce something called the Staines equation. And this is as follows. So you fix a function h, any function, such that this expectation is finite, and given h is given, we're going to find another function f, depending on h, which satisfies this simple linear differential equation. So in the left-hand side, I have f prime minus xf, and in the right-hand side, I have the h normalized, minus the expectation of h of z. Okay, so this is a very simple linear equation. It can be solved explicitly, and for example, there is a unique solution if you impose some decay at infinity, and the unique solution is given by this integral. So this is called the Staines equation, so you can solve this and you get this. And now what we're going to do is to replace here this x here by a random variable, then take the expectation, and then proceed. So suppose that you substitute x by a random variable, take the expectation, and then this previous relation here, you replace x by a random variable f and take the expectation. This is transformed into this equation here. So well, actually, this was the left-hand side, and this was the right-hand side. Okay. So you have expectation of f prime h of f minus f h of f is equal to this difference. Okay, and then on the other hand, it happens that if your function h is bounded by 1, then fh is bounded and it has a bounded derivative. So this is the bounded function is bounded by a square of pi over 2, and the derivative is bounded by 2. So now this allows immediately to obtain an estimation for the total variation distance between the law of f and the law of a normal 0-1 random variable c. So the idea is that you want to compute total variation distance between f and c. Remember, z is normal 0-1, f is an arbitrary random variable, so this by definition is the supremum with respect to the all-Borel sets b of this, and this is exactly this quantity when h is the indicator function of b. So using this equality, I can estimate this by the supremum of all these expectations, when here I take all functions which are satisfy these two conditions. which are bounded by 2 by a square root of pi over 2, and the derivative is bounded by 2. So this has nothing to do with Malliavin calculus. It's a general result, and it tells you that we will be able to estimate the total variation distance between f and a normal 0, 1 random variable if we are able to estimate this quantity. So now I'm going to assume now that f is a function of a Gaussian process belongs to a finite chaos. I'm going to use the formula we got before for this in order to get an estimate for the total variation distance. So that's the idea. So this is what we obtain. Suppose that f is in HQ for some q, is normalized, expectation is square root 1. Then this is what we wrote before. And now this quantity, if you remember the previous formula here below, if you use this, then you obtain exactly, you factorize f prime, you get a 1 because you have f prime, and you get minus 1 over q, the square norm of the f. So this comes from the integration by parts of Malliavin calculus, and the 1 is the one here. So on the other hand, the expectation of f prime of the square norm of f is q, and this turns out to be the variance. So if you use Cauchy-Schwarz, this is, and f is bounded by 2, so you get this estimate. Okay, so conclusion is that we can estimate the total variation distance between f and z by the variance, the square root of the variance of the square norm of the Malliavin derivative of f. So in other words, if the Malliavin derivative of f is small, the variance is small, it's close to a constant, then f is close to a normal random variable. And then working a little bit with multiple integrals and chaos expansions and product formulas, it turns out that this variance is equivalent to the difference between the moment of order 4 of f and phi. So there is this double inequality that can be proven using chaos expansion. Remember that f is in a fixed chaos. So all of these now can be used now to prove convergence to a normal distribution, and in particular, one can use the remarks that I have just given to obtain a very simple proof of what is called the fourth moment theorem that was proved by myself and myself in 2005, and later with a graduate student we added this condition in 2007. So the idea is the following: you fix Q, and now you have a sequence of random variables in a fixed chaos. And suppose that this sequence of random variables, the variance converges to sigma square, then these three conditions are equivalent. So the first is convergence in log to a normal distribution with variance sigma square. The second one is the convergence of the moments of order 4 to the moments of order 4 of the normal distribution. Then the third condition is that if you take contractions of the kernels Fn of order r, where r is the number of coordinates you contract, and you contract coordinates at least one and not all of them, then this goes to 0. So that's it's called the contractions condition. And then the fourth condition is that the square norm of the Malliavin derivative converts to a constant in R2. And the constant must be a q sigma square, actually. Okay, so this is what people call a fourth moment theorem. And for example, from this inequality I gave you here, and from this inequality, some parts of this equivalence follows immediately, and then the others are not difficult. Okay, so we make some remark about this. So this constitutes a kind of drastic simplification of the method of moments. You just have to carry about the moment of order 2 and the moment of order 4 in order to have convergence, but of course it only works for random variables in a fixed chaos, so with a fixed order of polynomial of fixed order. Then there have been some improvements. For example, this is a paper, interesting paper by Nualart and Piccati in 2013. They proved something called the optimal version of this fourth moment theorem, in the sense that they got also upper and lower bound for the total variation distance. And upper and lower bound is the maximum between the difference between the moment of order 4 and 3, which is what we got before, and the absolute value of the moment of order 3. So it turns out that the maximum of these two quantities is exactly the rate of convergence in the total variation distance. Okay? And this is for one-dimensional random variables. And Pecati and Tudor prove that the multidimensional extension, which can be also derived using Stein's method. Okay? Okay, there has been many applications of this theorem. I just will mention a couple of applications. For example, in a paper with Yao Tsong, we proved a central limit theorem for the renormalized self-intersection local time of the d-dimensional fractional Brownian motion with a parameter bigger or equal than 3 over 2d and 3/4 d is the dimension. That was one of the first applications of this theorem. I like to mention also some exact very asymptotics for functional Gaussian processes proved by Montel and Pecati. So they obtained the exact asymptotics for the difference of the distribution functions between Fn and Z, where Z is normal 0, 1 and Fn is function of a Gaussian process. And the exact asymptotics is given by phi of n, which is phi of n is the square root of the variance of the Malliavin derivative, and then there is also the third derivative of the normal distribution function, and then there is a constant rho, which is the limit of these quantities. But this is exact asymptotics in the sense that the ratio goes to 1. Okay, so this was also a result, and this is for random variables in a fixed chaos. But perhaps one of the most interesting applications is to recover in the way of getting a simple proof and getting a quantitative version of a classical result. For example, this famous Brouwer-Major theorem, in 73. So they were able to get some quantitative versions and some simple proof of this theorem. For example, this is a paper by Ivan Norden and Giovanni Pecati, and also Ivan Norden and Giovanni Pecati and Mark Podolsky. So what is this major theorem? So this is a kind of central limit theorem for functionals of a stationary process. And the statement is as follows. So you have a function f, which is a square integrable with respect to the normal distribution, and it can be expanded into mid polynomials. And then we assume that this function has Hermite rank t, where t is the first non-zero coefficient in the expansion. We call this the Hermite rank of the function. Okay? And then you take a centered Gaussian stationary sequence with unit variance, and rho is the covariance of this sequence. And then the assumption is that the series of covariance power t, where t is the Hermite rank, is convergent. So this is where the Hermite rank appears. The series of powers of the covariance at power t is convergent. Then we take a Vn, which is 1 over square root of n, sum of f of xk, and then this is the sequence we are interested in, and this converges to a normal distribution with a variance sigma squared, which is given explicitly by this quantity. So that's a classical result. There's also a functional version, of course, but that's a classical result. Goes back to 73, and I'd like to show you a very simple proof of this result using this fourth moment theorem, and in particular based on this condition using the Malliavin derivative. So how can you prove this kind of theorem? So the idea is the following. First, it's obvious to prove the limit theorem for every component, because then you have convergence in R2, and then it's obvious to consider one component. Convergence in R2, convergence of the variance, that's easy. Then you want to use Malliavin calculus. You have to build a Hilbert space. Hilbert space is the closure of all sequences with respect to this norm, which is associated to the covariance of the process. And then we can assume that xk is x of ek, where ek is the sequence which has 1 in place k and 0 otherwise. Okay? Then with these ingredients, then it suffices to show that the square norm of the Malliavin derivative of f converges to a constant in R2. If you prove this, then you can go apply the fourth moment theorem and you're done. How do you prove something like this? Well, you have to compute the square norm of the Malliavin derivative of f. Well, this f actually, I think it should be Bn. Okay. That is a typo here. This f should be Bn. Okay. Here it is. That's the sequence we are interested in. So this F is Bn, sorry. So this D of Bn actually is given by this formula. So there are some derivatives of the Arbic polynomial because you're taking a Malliavin derivative, and then there is this covariance. And then what happens is that when you look at something like this, you have 1 over n. So you can arrange the coefficients and then make a shift of, you call I minus j equal to n. And this has the same behavior in R2 as this quantity. Okay, that's very easy to show. So we just have extended this index from minus infinity to infinity. And now what happens is that if you look at this quantity as a function of j, this is very easy to show that this is a stationary ergodic due to the decay of the covariance. So now you have 1 over n, sum from j from 1 up to n of some stationary ergodic process. So you just apply the ergodic term, and you have convergence in R2 to the expectation, and that's what you want. So it's not surprising that we have proved a central limit theorem using the law of large numbers, which is the ergodic theorem. Okay, that's the idea. Okay, so I'm going now to change a little bit the topic, and so as everyone can see, that what we have in the fourth moment theorem is the convergence in total variation, which is strictly stronger than the convergence in distribution. That it's also one of the interests. So if you want a distance which is give the topology of the convergence in distribution, you can choose, for example, the Fortin-Fourier distance, which is the supremum of the expectations with respect to all functions which are bounded by 1, and you have a derivative of Lipschitz constant bounded by 1. Okay? So this is weaker than the total variation distance. Then it happens that if you are working on a finite sum of linear chaos, no matter what the limit is, if it's Gaussian or not doesn't matter, the convergence, and the limit is non-degenerate, then the convergence in low implies the convergence in the total variation distance. So you get for free a stronger way of convergence, provided that the limit is non-degenerate and the random variables belong to a finite sum of linear chaos. So this was proved by Nualart and Pauli, and this is the statement. Actually, the statement is quantitative. So you have a sequence of random variables. They belong to a finite sum of chaos. You assume that they converge in low, and the limit is not identically 0. Then the total variation distance is bounded by a universal constant times the power, which depends on p, of this Fortin-Fourier distance. So you are able to quantify this statement giving the power of this Fortin-Fourier distance. And the only thing you need is belonging to a finite number of chaos and to have a limit which is not identical to 0. The limit can be anything. So that's a general result that shows you that in some situations, convergence in low implies actually convergence in the total variation distance. Okay, so so this is for one-dimensional random variables. In a joint paper with Nualart and Pauli, we extended these to random vectors. So now you have a vector. The components belong to a fixed number of chaos. They converge to a limit. So the limit is a vector. So now here we need a more complicated condition on the vector, non-degeneracy condition. And the condition on the vector, on the limit, sorry, is that the limiting vector f infinity has a Malliavin matrix which has an expectation bounded below. So this gamma n here, it's a matrix, and this matrix is the matrix formed by the inner product of the derivatives of the components of f infinity. Okay? So of fn actually. So we want gamma n, which is the Malliavin matrix of fn, to have an expectation which is bounded below. This Malliavin matrix plays an important role in Malliavin calculus. For example, if you have a random vector and you want to know if it has a density, then the statistical condition is that the Malliavin matrix is not degenerate shortly. And you want to know that the density is infinitely differentiable, so this condition is that the determinant of the Malliavin matrix has negative moments of all orders. So the non-degeneration of the Malliavin matrix plays an important role in getting existence and regularity of densities in Malliavin calculus. So it's not surprising that here this lower bound on the expectation is the condition you need to get this type of result. So again, you have total variation distance bounded by this Fourier Fortet-Fourier distance to power gamma, where gamma is a complicated exponent. So why is this result true? So let me give you an idea of where we can prove this type of result. So the idea is as follows. To control the total variation, you have to compare expectations of bounded functions. To compute the Fortet-Fourier distance, you have to compare expectations of differentiable functions. So you have to approximate a function here, which is just bounded, by a function here that will be differentiable. So let me explain you briefly the technology to do this. Just a couple of ideas. So you take a function f, which is bounded, and you want to compute the expectation of phi of fn minus phi of fn. So f is bounded. So the supremum of these will give the total variation distance with respect to all bounded functions. But I want to estimate this by the Fortet-Fourier distance. So that the idea is I take the function f and I regularize with an approximation of the identity, rho alpha. And then I add and subtract and I get a residual term. Then this first term will be bounded by 1 over alpha, so it goes to infinity as alpha goes to 0, of course, times this Fortet-Fourier distance. But of course I get the Fortet-Fourier distance, but I get a coefficient that blows up as alpha goes to 0. And then what I want now is to control the speed of convergence to 0 of the residual as alpha goes to 0. But the residual is the expectation of this difference, and phi is just bounded. So I have no way to control this in principle. Okay, so now the idea to control this residual term, so I call H alpha the difference of phi and phi convolution of rho alpha. So what you do is you take this term, which is I call H alpha of Fn, and then you decompose this into these two parts. So remember that gamma n is the Malliavin matrix, so you take epsilon divided by the determinant of gamma n plus epsilon, and the determinant of gamma n divided by this. And the first one, okay, so the first one, I bound this by epsilon, this bounded by 1, or by 2, actually. And then you get the negative moments of this. And the second one, I keep it. So the idea is that for the first one, I will use this non-degeneracy condition we have. And then for the second one, we're going to use the Malliavin calculus, because for the second one, you have here the determinant, and this will help with the Malliavin calculus. So more precisely, for the first term, remember this is the first term, for the first term, you get that this goes to 0 at some rate. And this is based on this assumption, and then an inequality that was proved by a couple of analysts, Calgary and Wright, in 2001, and is very, very helpful. We're going to use this inequality also later. And this inequality tells you the following. You have, suppose that you have a polynomial Q of degree at most d, and then you have x is a standard Gaussian vector of some dimension. Then you can estimate the small probability for Q of x, so probability that Q of x is less than alpha, by a power of alpha, alpha to the power 1 over t, provided that the expectation of some power of Q is non-zero. So you can put this on the right-hand side. So this means that, essentially, if a polynomial on a Gaussian random variable, let's say a non-negative polynomial, has a non-zero expectation with some power, then automatically this implies that you have some small negative values for Q of x, automatically, for free. So using this inequality and using this non-degeneracy condition, that's the way we are able to get this estimate. So this was for the first term. And then for the second term, then you use Malliavin calculus. So I will not do the details here. So, but that's the typical way to use Malliavin calculus. And then you get epsilon power minus 2, this comes from the epsilon here. And then you have a power of alpha power, positive power. So here is what we wanted, the rate of convergence to 0 as a power of alpha for this term. Of course, now you have several parameters. You have epsilon, alpha, you have also an n, you have to assume that n is bounded, so you have to optimize these parameters and play with these parameters, and then that's the way you get the result. So this is a brief idea of how to prove this type of result. And then if you ask what are the specific conditions for this non-degeneracy condition, for example, if you have convergence to a normal, then this is always true. Because for the fourth moment theorem, we know that in that case, the Malliavin matrix, the Malliavin matrix converges to the covariance matrix in R2, and then automatically you have this if C is non-degenerate. Then we have proved also that this is true in the case of a vector with independent and non-degenerate components. And also this is true in case we have convergence in R2, not just convergence in law, because in that case you have convergence of the expectation of the determinant of the Malliavin matrix, and then in that case, well, this is true provided that the determinant of the Malliavin matrix in the limit has non-zero expectation. And this is equivalent to this old theorem by Kusuoka, that this tells you that this is equivalent to the fact that F infinity has an absolutely continuous distribution. Okay? So these are some sufficient conditions to have this non-degeneracy condition. How much time do I have? 8, okay. So I'm going to go a little fast to the last part of my talk, which is convergence of densities. So the total variation is the L1 norm of the densities. Assume that your random variable has a density. Call it P sub F. So convergence in total variation is exactly convergence in L1. So the question is, can we have something different? For example, uniform convergence of densities. So pointwise or uniform convergence of densities is important in some applications. So we like to have this. Then, of course, as I told you, condition in Malliavin calculus to have a density is to have negative moments for the Malliavin matrix. So now it's natural that here we need a condition of this type. So negative moments of d of f, and here the negative moment we need is a 6. If this condition is true, then you have this inequality, which gives you an upper bound, which is exactly the upper bound we got for the total variation distance, but now for the uniform distance of the densities. Okay? And this for random variables in a fixed chaos. This was proven in a joint paper with Yao Hu and a graduate student, Lu Fei. And this was later, P6 was improved to -4 minus epsilon in a joint paper with Nurdeng, where we used the notion of Fisher information. And we improved a little bit the exponent. How can we prove something like this? So I'm not going to give you details of this, but the basic ingredient is this formula. This is a formula, basic formula in Malliavin calculus, which gives you an explicit expression for the density of a random variable in terms of these Malliavin operators. So you take d of f, divide by the square norm of d of f, take delta of this, multiply by the indicator function. This is exactly the density. And once you have this, you compute delta, I mean, use rules of the Malliavin operator, you get 2 terms, and you use that f is in the chaos of the q, you get qf here. Then remember that when f is Gaussian, the density, the square norm of the derivative is a constant. So what we are going to do is to replace this square norm by 1, or by q actually, and you get this term, and you get now these 2 terms. Now these 2 terms is easy to prove that they can be estimated by this, and then the first term, you compare this now with the same thing with z, and now a simple exercise in probability theory tells you that if you have a Gaussian random variable can be written in that way. And then you estimate this difference, and this can be done again by stage method. So that's a very quick sketch of proof. And some examples. So this is an example in the second chaos. Condition is that, so this is an example which is useful when you know the eigenvalues of the operator for the random variable in the second chaos. But, and then this quantity, sorry, this quantity in this case turns out to be equal to the sum of the power 4 of the coefficients. But this example is not very much interesting because first, usually you don't know the lambdas in some interesting examples, so you're not able to apply this example. But I have a more interesting example, which is again the Brouwer-Marshall theorem. So we go back to the Brouwer-Marshall theorem, remember, and now here I'm going to assume that the function f, which has an expansion in the real polynomials, is an expansion which goes from d, which is the meter rank, remember, to some q. So it belongs to a finite chaos. Then in that case, assuming very mild conditions on the Gaussian process, the only condition is that the log of the spectral density is integrable, which is, remember, that's the condition that allows to have a causal representation for your process. And then, of course, we need this type of integrability. Then in that case, you have negative moments of any order for the norm of the derivative of Vn. Okay? And in particular, if you are in a fixed chaos, so if q is equal to d, then you get an estimate uniform estimate of the density of Fn, where Fn is Vn normalized by this moment of order 4. Okay? So the proof of this, again, how do you get these negative exponents? The proof of this, again, is using this Carpenter-Wright inequality. So what you do is you compute the Malliavin derivative, and then this turns out to be a sum of the squares, or bounded below by sum of the squares, and then you do a kind of block decomposition. So that's a sum from 1 to n, and then you decompose this into small blocks of size n over n. And then when you take a negative power of Bn, this can be bounded by a negative powers of the over P over 2n, where n is the number of blocks. Now, if you take a big number of blocks, if n is big, so the number of blocks is big, you're going to get here a small power. And I told you before that Carpenter-Wright inequality is a very helpful tool to get small negative powers of a polynomial. Well, this is not exactly a polynomial, but you can more or less arrange this. So the idea is that using the composition into blocks, you reduce the problem of a negative moment to a very small negative moment, and then you apply this Carpenter-Wright inequality. That's more or less the idea. And basic example is increments of the fractional Brownian motion, which is a Gaussian process with these covariants, and then the covariance satisfies this condition. So when you take a mid polynomial and you take these mid variations, then you can apply the previous theorem to this mid variation, and this RMD condition here is translated into h less than 1 minus 1 over 2 cube. That's exactly this condition on the convergence of the series of the covariance power d corresponds to this condition on h. So now we can apply the theorem, and then we can apply the previous theorem, and you take the uniform convergence of densities for any mean variation, and in particular for quadratic variations. Then this is a paper by Pierre Medon and Leon. They computed this rate, and it turns out to be, well, the rate of the central limit theorem up to 5 over 8, and then it gets worse until 3/4, and then at 3/4 it gets 0 because h must be less than 3/4. Okay, so that's a simple example of application. And now, well, there are some generalizations. For example, we can show not only convergence of the densities, also convergence of the derivatives of the densities, provided you have negative moments of high order. And you can consider also vectors. And if you have negative moments of the determinant of the Malliavin matrix, then you have uniform estimates for all derivatives of the density by the derivatives of the normal standard distribution. And this is in terms of, again, differences, variance of the moments of order 4, and then see the covariance matrix of F minus identity. Okay, so that's a kind of, this is in our paper with Yao-Tsung Hu and Fei Lu, and we have obtained these generalizations. Now, to conclude, I'm going to talk about how to generalize this when we don't have a central limit theorem, but we have a non-central limit theorem, which means that the limit is a mixture of Gaussian distributions, which means that the variance is Riemann. So in that case, you have this notion of stable convergence, and then the question is, can we apply this technology to get greater convergence when you have convergence to a non-Gaussian distribution? Okay? So there are many examples where this kind of external noise appears. For example, fluctuations of the error in approximation schemes for stochastic differential equations, weighted or mean variations of stationary Gaussian processes. So it's similar to what we have seen before, but with a weight. Then there are several papers recently on central limit theorems, actually I should say non-central limit theorems, for the second and third moments in space of Brownian local time increments. And there are many other examples where the limit is not Gaussian, is a mixture of Gaussian distributions. Then it turns out that in this situation, well, we don't know how Weierstein's method works, and actually I think we haven't been able to apply these ideas on Weierstein's method because the variance is random, so things are much more complicated. But there's a recent paper that I wrote with invariable and geometric identity, where we use an interpolation method and Malliavin calculus, and we obtain some general results on rate of convergence. I'm not going to give you the results, but I will give you just one example where these results can be applied, so this will be my last slide. So the example is this quadratic variation of the fractional Brownian motion, but with a weight. So if you don't have this term, this is what we have considered before. So now we have a weight. The weight is the value, is a function of the value of the fractional Brownian motion in one of the two intervals. So this is a kind of Riemann sum. So you take the value, you take a partition, and you take the value, the function f of the value of the fractional Brownian motion in one interval, and then you multiply by this limit variation. Okay, so now what happens with this? Then in that case, the limit of this as n goes to infinity is not normal, is of the form s times eta, where eta is normal 0, 1, and s is a random variance. Well, actually, s squared would be the variance, and the variance is a constant multiplied by the integral of f squared bh s ds. So this was known, but what we have done is the following. We have obtained a rate of convergence in the sense that we take a test function phi belonging to a very small class of test functions, in the sense that you need 5 derivatives. So that's a very small class of test functions. And then we estimate this by some universal constant, depending on f and h, then the maximum of the infinity norm of this is 5 first derivative, and then the rate is measures the distance between h and 1/4 and 3/4. And it turns out that the rate is optimal when h is 1/2, which is the Brownian motion, and it goes to 0 in the boundary points. And this is natural because when h is 3/4, you don't have a limit theorem, because then you have convergence to the integral of the Rosenblatt process. You have this Rosenblatt process appearing at 3/4, and you have convergence to the integral of the Rosenblatt process. And when h is less than, when h is less than 1/4, then it was proved by Norden that the limit is 2. The normalization is different. It's not 1/square of n. So it's a completely different phenomenon. So really, these two boundary points are, you cannot go behind this further. And then the fact that you have this symmetric rate with respect to these two is kind of surprising. And this is just for the quadratic variation, so we hope to get similar results maybe for other weighted variation, or even for more sophisticated examples where the limit is a mixture of Gaussian distributions. So I think that I'm going to finish with this example. Thank you very much for your attention.